the part 2 video of the Honors Chemistry section 17.4 lesson video. So this is part 2. Remember, if you want all my videos in one place, just subscribe and you'll have them all there. So we're going to pick up where we left off. So if you watch the section 1 video or the section 17.4 video part 1, then you already saw how to do Hess's Law and standard heat of formation. So we're going to continue on with a little bit more standard heat of formation, just based on them asking you varying units to come up with, being able to write your own reactions, and then solving for a standard heat of formation for a substance instead of for the whole reaction. And then we'll wrap it up and do our section assessment and our sample integrative exercise. So hopefully this video won't be too long, but after I just said all that, I feel like it's going to be. So it says, calculate the standard enthalpy change for the combustion of 1 mole of benzene, which is C6H6 liquid, to form CO2 gas and H2O liquid. Now this is the important part. Remember, the standard heats of formation are different for the different states of matter. So if they didn't tell us whether we're forming water liquid or water gas, sometimes that can be kind of tricky. Alright, so we have to write our reaction because they didn't give us one this time. So C6H6 liquid. We're doing combustion, so remember, combustion means something burning in the presence of oxygen gas, and then it forms CO2 gas and H2O liquid. So we have to have the coefficients because you know how we multiply by the coefficients when we're solving these, so we have to balance it. So I have 6 C's, 1 C, so I'm going to put a 6. I have 6 H's, 2 H's, so I'm going to put a 3. And then I have 2 O's. Here I have 12 and then 3, which is 15 O's. Okay, so as I always say, what I like to do is double the reaction. So I'm going to change this to a 2, this to a 12, and this to a 6. So that keeps everything balanced. 12 C's, 12 C's, 12 H's, 6 times 2, which is 12 H's. So now we can get an even number of oxygens, because that was the problem. We had an even number on the side and then 15 on the side. So now I have 24 right here plus 6, which is 30. So 30 divided by 2 is, of course, 15. So we're doing the standard enthalpy change for the combustion of, and here's the important part, 1 mole of benzene. How many moles of benzene do we have in our reaction? 2. Okay, so you can do one of 2 things. You can reduce your reaction and do 1, 7.5, 6, and 3 if you want to. I personally don't like seeing decimals or fractions in a reaction if possible, so I'm just going to divide my answer once I get there. Alright, so remember, your delta H is products minus reactants. So let's just plug in. So my products are CO2 and water. So I have 12 CO2, so I'm going to do 12 times, and that's CO2 gas. So remember the charts page we discussed. So I find CO2 gas, and it's negative 393.5 kilojoules. Remember, we dropped the moles because we're technically multiplying by 12 moles. I just don't write it out every time. All right, we also have 6 moles of liquid water. So I'm going to do 6 times my liquid water, which is negative 285.8 kilojoules. And so there I took care of my products. So products minus reactants. So I have 2 C6H6 liquids. So I do 2 times. So I find my C6H6. Oh, it's not on my paper. I must have looked it up online then. Let's see what I found online. I found 49 kilojoules. So see, that's the thing, is if you find a number that's not on your charts page, sometimes I'll put it in the question, sometimes you can just Google it. Remember, these aren't secretive numbers that I come up with. You can find them anywhere. And then, of course, plus my 15 times my oxygen gas. But remember, O2 gas is its natural state, so it's technically 15 times 0 kilojoules. Most of y'all, you just wouldn't write oxygen in there at all. Alright, and so then once I solved for that, I ended up getting negative 6,533 kilojoules. But remember, this happens for the reaction exactly as the way it's written, which is for 2 moles of C6H6. They're asking for the heat change that occurs with 1 mole. So what would I need to do here at the end? I would need to divide by the fact that it's really per 2 moles. And so I get the 2 because of this right here. And so what my actual delta H should be is negative 3,267 kilojoules, and then I put per mole of C6H6. Okay, so if you don't reduce your coefficients to give you 1 mole of benzene, you need to make sure to divide by that coefficient at the end, because they're very specific in wanting 1 mole. Alright, so part B says, compare the quantity of heat produced by the combustion of 1 gram of propane to that produced by 1 gram of benzene. Okay, well first let's switch over to propane. So propane is C3H8, and we are doing combustion, so we're going to have plus O2, and we're going to yield CO2 and H2O. Alright, so on this one, again, we're going to assume that we're also creating liquid water because it didn't tell me any different. Oh, whoops, sorry, I forgot to put my propane gas right there. We'll assume that we're going to liquid water because it didn't say any different. And so first we need to balance. So I have 3 C's, so I'll put a 3 here. I have 8 H's, so 4 times 2 is 8. And then I have 2 O's on this side. Here are 6 and 4 more, which is 10. So I would put a 5. Now the thing we have to be careful of is, notice on this one we're talking about 1 gram of propane and 1 gram of benzene. So see up here we have per mole of benzene. So we're going to have to address that, and we'll have to address it on this one too. Hopefully I'll have enough room. I may have to erase in the middle of it. So remember, our delta H is products minus reactants. So let's start with our products. So we have 3 CO2 gas. So I put 3 times. And then I'm going to find my CO2 gas on here, and it's negative 393.5 kilojoules. Alright, so I took care of that. And then we have 4 moles of liquid water. So I'm going to do 4 times my liquid water, which is negative 285.8 kilojoules. So I took care of, those are my products, minus reactants. So I only have 1 mole of propane. C3H8, look, that's not on my charts page, so again, I would have looked this one up. And so it's negative 103.85 kilojoules, so that's propane. Plus, of course, my oxygen 2, O2 gas, that's the natural state, so 5 times 0 kilojoules. So once I solve all of that, I ended up getting negative 2,219.85 kilojoules per mole of C3H8. Okay, so on this one, I went ahead and changed to per mole of C3H8 because I know I'm going to have to get to grams. And the reason I could already do per mole on this one was because it really was per mole. There's only 1 of those. Up here I had to divide by 2 because it had a 2 in front. Alright, so now all we need to do is convert these to kilojoules per gram, because that's what it's really asking. Compare the heat produced by 1 gram of propane to 1 gram of benzene. Okay, so I'm going to erase some of this. I'm just going to leave my answers up so that we can convert from there. Alright, so here's my answers, so I at least have something to go by. Alright, so we're starting with, let's just do benzene first because I have that one up here first. So we have 1 gram of C6H6. So the first thing I'm going to need to do is get that to moles, because see, this is per mole of benzene. So I'm going to add up the molar mass. So when you add up C6H6 off the periodic table, you get 78 grams in 1 mole. And then once I have that, I can multiply by my number. So negative 3,267 kilojoules per 1 mole of benzene. So my grams cancel, my mole canceled, and when I solved, I got negative 41.88 kilojoules. In this case, we're talking about per gram of C6H6. Okay, so 1 gram of benzene releases that many kilojoules. Alright, so now we got to do propane. So I have 1 gram of propane, which is C3H8. So I've got to do molar mass first. So when you add up C3H8, you're going to get 44 grams in 1 mole. And then I can multiply by my heat. So negative 2,219.85 kilojoules per mole. So my grams cancel, my moles cancel. And so I get negative 50.45 kilojoules per gram of C3H8. So in other words, per gram, the propane is going to release more energy because it's negative 50, whereas the benzene's only about negative 42. Alright, so let's move on to another type. So this was about let me let you try one probably. About manipulating units And by manipulating units, I mean questions like this, where you know what to do, but then you got to fix the units to what they're asking for. And then we'll look at how to solve for one of the substances. Alright, so it says, using the standard enthalpies of formation listed in table 5.3, we'll just be using these / anything we need to look up off the internet. Calculate the enthalpy change for the combustion of 1 mole of ethanol. So this one's normal because how many moles of ethanol do we have? We just have 1 mole of ethanol. So we just need to do our products minus reactants. So if you want to pause and try this one, that would be a good idea. But we'll look at it together. Alright, so I do my products. I have 2 moles of CO2 gas. So I'm going to do 2 times, and then I'm going to look up CO2 gas. So negative 393.5 kilojoules plus my 3 H2O liquid. So I do 3 times, and my H2O liquid is negative 285.8 kilojoules. Alright, so there are my products minus my reactants. So I have C2H5OH, which of course is not on my charts page. That means I had to look it up. So C2H5OH I found was negative 277.7 kilojoules. And then I'm going to add to that my O2 gas, which as always is 0. So I'm going to do 3 times 0 kilojoules. And so when I solved, I got negative 1,366.7 kilojoules. Now they did ask for 1 mole of ethanol. Well, is it 1 mole this time? Yes. So we can just say per mole of C2H5OH. So since they asked per mole and we were solving for a 1 mole reaction anyway, then that's our answer. Alright, so let's look at what happens if I give you the heat change, but then I ask you to solve for one of the substances. So it says the standard enthalpy change for the reaction is, of this reaction, is 178.1 kilojoules. So we know the delta H for the whole reaction. So like our delta H is 178.1 kilojoules. From the values for the standard enthalpies of formation of CaO and CO2 given in table 5.3, calculate the standard enthalpy of the formation of CaCO3. So in other words, we're looking for the the standard heat of formation for CaCO3. Alright, so what we need to do is just remember delta H equals products minus reactants. So we just plug in what we know. Well, now we actually know delta H. Delta H is 178.1 kilojoules. Alright, so we know that. So then we're going to do products minus reactants. So one of my products is CaOS. So I use my charts page. I find CaO solid, and it is negative 635.1 kilojoules. Alright, I also have CO2 gas, and notice they both have 1s in front. So CO2 gas is negative 393.5 kilojoules. And then I'm going to subtract my reactants. Well, my reactant is what I don't know, so I'm just going to put minus X. And it's just 1X because, of course, there's no coefficient. Alright, once you do that, all you have to do is solve for X. So you'll combine these two, get it on the other side, and so once you solve for X, you end up getting X equals negative 1,207 kilojoules per mole. Because remember, the delta H is for each individual substance. It's always given in kilojoules per mole. Alright, so we just solved that for X. That's all I did was combine these two values and then moved it on to the other side by changing the sign. Alright, so hopefully that wasn't bad. It's just basic algebra. So you try this one. So just pause it real quick, try it, and then we'll look at it together. So it says, given the following standard enthalpy change, use the standard enthalpies to calculate the standard enthalpy of CuO solid. So we're looking for CuO solid. Alright, so we know delta H equals products minus reactants, but this time we know delta H. It's negative 129.7 kilojoules. Alright, and that equals our products minus our reactants. So copper solid is its natural state. So it's going to be 0 kilojoules. That one's easy enough. Water liquid. So I'm going to look at my thermochemistry charts page. It is negative 285 0.8 kilojoules. And again, I didn't have to multiply anything because they're both coefficients of 1. All right, minus my reactants. So we don't know CuO, so I'm going to put in an X. And then H2 gas is its natural state, so 0 kilojoules. And so then all I do is just solve for X. Okay, so I have X here. Keep in mind it is going to be a negative X, so you're going to have to change the sign. So I would combine these two, move it to the other side, change the sign, because of course I'm technically solving for negative X right here. And so then once I solve for X, I ended up getting that X equals negative 156.1 kilojoules per mole. All right, so hopefully you got that one right. So let's move on. So section, whoops, uh-oh. I'll be looking at my answer. All right, so section assessment. Let's knock this out real fast because I'm sure this video is like 4,000 hours at this point. All right, so here's the reaction we're trying to get to. Here's our 3 to alter. All right, so if you look, 2 of them have O3, so I don't want to look at that. They all have, or these 2 have O2. These both have O2. So in the first one, I could look at either of these. So I'm going to pick NO to look at. All right, this one, it has substances from both the other reactions. That means that it's there most likely to cancel things out. Because if you notice, O3 and O2 are not in our final reaction. So this reaction is given just to cancel things. All right, and then O2 is in another reaction, but O by itself is not. So I'm going to focus on O. All right, so on our first one, we have NO, one of them as a reactant. I want one as a reactant, so I'm going to leave the first reaction the same. Oh gosh, I'm going to have to write kind of small again. Sorry about that. I don't leave myself a lot of room up here. If I leave the reaction the same, of course, I'm going to leave my delta H the same. All right, the second one is used to cancel things. I'm going to skip it for right now so I can figure out what I need to cancel in a minute. All right, so let's look at our second one. So we have 2 O's as a product. I want 1 O as a reactant. So that means I need to flip it and divide by 2. So that means I need to change the sign of delta H and divide it by 2. All right, so remember when we flip it, we write the products first, but I'm also dividing by 2, so I'm going to write O and then 0.502. And so again, for delta H, I'm going to change the sign and divide it by 2. And so when I did that, I got negative 247.5 kilojoules. All right, so on here, this is where you have to be careful on the canceling ones. So like I'm just going to look at O3 because I don't want to deal with that fraction. All right, so we have O3 as a reactant. We don't want O3 anywhere. So let's look at where we have it down here. We have O3 as a reactant, but we don't want it. So how can we get it to cancel? Well, we could put it as a product. Okay, so what we're going to do is we are going to flip this reaction, which means we're going to change the sign of delta H. All right, so if I flip it, then I'm going to have 3 halves, or let's change it to 1.502, yields O3. All right, because we're going to flip it. And so then we change the sign of our delta H so it becomes positive 142.3 kilojoules. All right, so all we use the last reaction, or really the second reaction for, is to cancel that O3 that we don't want anymore. So if you look, the O3 is going to cancel. All right, let's look at that O2. So here we have 0.5 and 1, which is 1.5, and we have 1.5. So that's going to cancel. And then we write what we have left. So NO plus O yields NO2. Is that the reaction we want? Yes. So we add up those delta H's. So my delta H, once I add those up, I ended up getting negative 304.1 kilojoule. And that's my answer. Okay, so when you get a reaction where neither the reactants or products are in your final equation that you want, it's used to cancel out things that you don't want. All right, so let's look at one more standard heat of formation, and then we'll do our sample integrative exercise. Hope that my camera battery will even last this long. Maybe I'm going faster than I think, but I highly doubt it. All right, so it says, what's the standard heat of reaction for the decomposition of hydrogen peroxide? All right, so remember, we know that our delta H is products minus reactants. So we get our thermochemistry chart page out. All right, we have 2 moles of water as a liquid. So I'm going to do 2 times H2O liquid is negative 285.8 kilojoules. And then of course we have oxygen as a gas, O2 gas, so that's 0 kilojoules, minus our reactants. So we have 2 hydrogen peroxide, H2O2 liquid. So I'm going to do 2 times negative 187.8 kilojoules. Alright, and remember these numbers, they're just coming from thermochemistry charts page or online. Like I said, there were a few I probably had to look up. And so when I solved, I got negative 196 kilojoules. Alright, so hopefully you're feeling a little more comfortable with Hess's Law and standard heated formation. So let's look at our sample integrative exercise. Alright, so there's going to be a lot of information. So trinitroglycerin, there's your formula, usually referred to as nitroglycerin, has been widely used as an explosive. Alfred Nobel used it to make dynamite in 1866. Rather surprisingly, it is also used as a medication to relieve angina, which is chest pains, resulting from partially blocked arteries to the heart by dilating the blood vessels. The enthalpy of decomposition at 1 atm pressure of trinitroglycerin to form nitrogen gas, carbon dioxide gas, liquid water, and oxygen gas at 25 degrees Celsius is negative 1,541.4 kilojoules per mole. Okay, so they're giving me the delta H right here. Alright, so I'm probably going to need that number in a minute, but I have it on my paper, so I'll just look there. Alright. So it says, write the balanced chemical equation for the decomposition of trinitroglycerin. Okay, well first of all, I have all the information I need right here. It gave me the formula, and then it gave me what it forms. Nitrogen gas, carbon dioxide gas, liquid water, and oxygen gas. So I start with my formula for trinitroglycerin, which of course they told me is C3H5N3O9, and we are decomposing it, and it says we make nitrogen gas, we make carbon dioxide gas, we make liquid water, and we make oxygen gas. Alright, so we need to balance this thing. This thing is a little tricky to balance, I will tell you that. Alright, so we have 3 C's, so I'm going to put a 3 here. We have 5 H's, and here I have 2. So I have odd and even, so I'm going to go ahead and double this to make it even. So that means I'm going to have to change this, because now I have 6 C's, so I'll put a 6. Now I have 10 H's, so 5 times 2 gives me 10, so I fixed that whole odd number issue. I have 6 N's right here, so 3 times 2 is 6. And then of course, if you've done any balancing, you know oxygen always messes everybody up. I have 2 times 9, which is 18 oxygens. Here I have 6 times 2, which is 12. 5 times 1, which is 5, and 2 more. So I have 17, 18, 19 oxygens. Oh my gosh, seriously? So we have 1 too few on this side. There's no way to fix that. So what do I always like to do when stuff isn't working out? Double it. So let's just double everything. So 2 is going to become 4. 3 is going to become 6. 6 is going to become 12. 5 is going to become 10. And I don't really know what goes here yet, so I'm just not going to put anything. Alright, so now let's look at oxygen. Because everything else, if I double everybody, everything else remains balanced. So now I have 36 oxygens. Here I have 12 times 2, which is 24. I have 10 times 1, which is 10, and I have 2. 24 plus 10 is 34, plus 2 is 36. So everybody's balanced. Remember, when in doubt, just start doubling everything. And that's usually the best way to do it. Alright, so it says calculate the standard heated formation of trinitroglycerin. Okay, so if you remember on the previous slide, like I'll go back real quick, they told us the delta H for the reaction. Okay, so see, that's where you gotta be careful, is you gotta use information that you already know from previous reactions. So remember, delta H equals products minus reactants. Alright, so I'm gonna start with my negative, I'm pulling this from the previous slide, negative 1,541.4 kilojoules per mole. That's what they gave me. But in our reaction, how many moles do we actually have? We have 4. Okay, like once we balanced it, we got a 4. So I'm actually going to need to multiply this by 4. Okay, because remember, the delta H has to be for the way the reaction's written. This is per mole. We actually have 4 moles. So let me write moles here so you know why I'm doing that. Alright, and so once I multiply, I get negative 6,165.6 kilojoules. So now that's what I can use as my delta H. All right, so my delta H is negative 6,165.6 kilojoules. And then, of course, that equals my products minus my reactants. So, oh my gosh, there's a lot of products here. So we have 6 times nitrogen gas, but nitrogen gas is natural element, so it's 0. All right, we have 12 carbon dioxide gas. So I'm going to do 12 times, and then I'm going to look up carbon dioxide gas, which is negative 393.5 kilojoules. All right, we also have 10 liquid waters. So I'll do 10 times liquid water is negative 285.8 kilojoules. And then I have O2, which of course is 0 kilojoules because it's in its natural state. And then all of that minus my reactant, which is my C3H5N3O9, my trinitroglycerin. Alright, but you got to be careful on this because we're not just going to put X because what's in front of it? A 4. So we're actually going to solve this for 4X. Okay, so you got to be careful of that. We haven't done one where there was a coefficient on what we're solving for, but if there is, you have to put that coefficient there. Alright, so then I'm just going to combine all my like terms, get them onto the other side, solve for 4X, and of course, keep in mind it is a negative 4X. So I'm going to divide both sides by negative 4 at the end. And so once I solved all this, my X was negative 353.6 kilojoules per mole. Alright, so hopefully you can follow all that. I know that was a lot of numbers. And I'm going really fast because this video is super long. My planning period is going to end in a minute. Alright, so let's move on and see what's next. What else could this question possibly want to know at this point? Just trying to beat the bell at this point. Alright, so it says a standard dose of trinitroglycerin for relief of angina is 0.6 milligrams. If the sample is eventually oxidized in the body, not explosively though, to nitrogen gas, carbon dioxide gas, and liquid water, what number of calories is released? So in other words, we're starting with 0.6 milligrams. We're trying to get to calories. Okay, so we have our 0.6 milligrams. Well, of course, our first step would be, we don't work with milligrams very often, so to get to grams. So 1,000 milligrams equals 1 gram. And then, of course, our next step would be we need to get to moles. Okay, so 1 mole of our trinitroglycerin, when you add up the molar mass, you should get 227 grams. That was just me adding up the trinitroglycerin formula from the periodic table. All right, and so then I'm going to use that number that they gave me on the first slide, where they gave me the negative 1541.4 kilojoules per mole. I just pulled that from the first slide of the question. Okay, that got me to kilojoules, but the problem is they want the answer in calories. Okay, so then, boy, I hope you love converting like me, because this problem, I'm all over this thing. I love converting, but I know most of y'all probably don't. So 1 kilojoule, of course, is 1,000 joules. And then, of course, 1 calorie is 4.184 joules. Oh my gosh, look how awesome that is. All right, so once I solved all that, I got negative 0.97 calories. But notice it said how many calories is released. So you could put the negative 0.97 calories, or you could just say 0.97 calories is released. Because if you say something is released, then that is to assume it's negative from the point of view of the system. All right? So, oh my gosh, the bell rings, so let me hurry. So, one common form of trinitroglycerin melts at about 3 degrees Celsius. From this information and the formula of the substance, would you expect it to be molecular or ionic? Oh my gosh, I'm sorry, we'll just keep going. Well, if it has a low melting point, which it does, 3 degrees Celsius, we would consider it to be molecular. Okay, so we would consider molecular because of its low melting point. Okay, so for part D, it's molecular because of its low melting point. Oh my gosh, this is so wonderful.
Ashley Relaport, Jose.
Alright, and then it says, describe the various conversions of forms of energy when trinitroglycerin is used as an explosive to break rock faces in highway construction. So there's lots of different forms of energy that you could list. I talked about chemical potential energy in the reaction itself. I said that it would change into heat because, of course, you know when there's an explosion, there's usually fire. Combustion usually produces a lot of heat. I said that you would also see a lot of light energy because, of course, those are energy conversions. I said that we would see some kinetic energy because, of course, we're moving rock.
Hannah Kyler Reese, come to the attendant's office. Hannah Tyler Reed. Come to
All
the
right,
attendant's
based on the
office.
excessive announcements, I would say we'll stop with those energy changes. And so that is section 17.4, part 2. So hopefully, like I said, you've got Hess's Law and standard heated formation under control.